In Alaska and across northern Canada, to Norway and northern Siberia, during the months when nights are dark and clear, the aurora lights the sky. During the course of a night, the northern lights often follow a typical pattern, beginning in the early evening with a diffuse glow to the north. Slowly, they form a gentle arc that can stretch from one horizon to the other. Within a short time, they begin to move, like a curtain blown by a breeze. The arc may develop vertical rays that ripple and change color. Often after midnight, the aurora moves overhead and intensifies, folding and twisting, sometimes exploding with colors that race across the sky. Then, after a few minutes of violent activity, the aurora scatters and seems to disappear. But actually it is just spread out across the sky, forming large cloud-like patches. These pulsate on and off and may continue for 2 or 3 hours before gently disappearing. Some nights, during times of intense auroral activity, this sequence may occur 2 or more times. Time and time again, as they pursue ordinary chores during the long winter nights, people of the far north are distracted by the dance of the Aurora Borealis. And even to longtime observers, what sparks this remarkable light show has long been a mystery. Many people have wrongly believed that the aurora is a reflection of sunlight off ice crystals in the sky. Others say they can smell electricity in the air during auroral displays. And there are those who claim they can actually hear the aurora, that it produces a quiet swish or faint crackling sound, usually during the times it moves rapidly overhead. Scientists are puzzled by these reports because attempts to record auroral sounds have failed. Eskimo myths even say that if you whistle at the northern lights, they'll swoop down and get you. Perhaps there will always be mysteries associated with the aurora, but there are well-documented scientific theories about what causes the phenomenon. Many of them come from the pioneering efforts of auroral researchers at the Geophysical Institute on the campus of the University of Alaska, Fairbanks.
This next slide is from a Dynamics Explorer satellite.
Physicist Neil Brown has been studying and explaining the aurora for nearly 3 decades, yet the formulas in physics sometimes take a back seat to its sheer beauty.
To this day, if there's a spectacular aurora, I'll still stop dead in my tracks. I'll pull over to the side of the road. In fact, a couple of years ago, I pulled over the side of the Steese Highway at 2 o'clock in the morning and just shut the whole car down and laid down on the road and watched the aurora because it was just so incredibly beautiful.
But what causes these fascinating displays? For decades, Brown and his colleagues have been pursuing and finding the answers.
The aurora, those lights in the sky, the bottoms of them are about 70 miles above the Earth, and they represent a gigantic electrical discharge in the Earth's atmosphere, just like drawing a spark with crossing a couple of electrical wires, or perhaps a static electricity when you walk across a carpeted floor on a dry winter's day and you reach over to touch the doorknob, and you'll hear the little electrical snap, but sometimes you also see that little snap of light. In its simplest, the aurora is an electrical discharge, just as simple as that.
A neon sign can be thought of as a controlled aurora. The glass tubes contain some neon gas in what otherwise is a vacuum. The gas is bombarded by a steady stream of atomic particles, causing billions of tiny collisions and creating light. In much the same way, the aurora is caused by energetic particles bombarding the atmospheric gases high above the Earth. A postdoctoral fellow at the Geophysical Institute, Gina Price has been studying the collisions that spark the auroral light as part of her research.
The charged particles first start colliding with the particles of our atmosphere up at about 400 kilometres, which is about the top of the very tallest rays of the aurora. As they get closer to the Earth, the atmosphere is getting thicker and thicker. By 200 kilometres, there's a substantial amount, and that's where we see a lot of the red in the aurora. As they get closer, the atmosphere is getting thicker and thicker, and by 120 kilometres, it's very thick, and that's where most of the emission from the aurora is. Below 100 kilometres, it's too thick for the particles to penetrate, and so that defines the bottom of the aurora. So the auroral rays go from about 100 kilometres up to 300 or 400 kilometres.
If you were somehow able to drive a car straight up from the Earth's surface to the aurora, it would take you an hour to reach the very bottom of the lights. That's at an altitude of about 100 kilometers or 60 miles. To reach the top of the tallest rays, you'd drive another 3 hours, reaching an altitude of 400 kilometers or 240 miles above the Earth.
You can think about the particles that are raining down from space in a sense of like a pinball machine. Now, in a pinball machine, you grab a hold of a plunger and you pull it back, and that fires the ball up into the top part of the machine, and then it falls back down through the machine. And as the pinball courses down through the path of the machine, hitting and bouncing off various targets and creating light each time, so does that particle raining in the Earth's atmosphere hit atom or molecule and create light, and then go further or deeper into the atmosphere and again create more light until it's finally stopped.
The colours in the aurora are caused by the different gases in the atmosphere. When the particles collide with nitrogen, we get red colours and blue colours. When they collide with oxygen, oxygen can give off a red and green. It's all dependent on the structure of the different gases, on their atomic structure.
Just as targets on the pinball machine give off different colors when hit, so do atoms in the atmosphere.
The oxygen gas in the atmosphere is the gas that's responsible for the main two colours in the aurora. The red that we see up in the top of the rays and the strong green that we see down at the bottom. Now, the reason that we see two colours given off by the same gas is because of the density of the atmosphere.
Just as the colors of the aurora depend on the types of gases struck by electrically charged particles, the colors of neon signs depend on the type of gas inside the tube. Neon gas, hit with electricity, produces a typical red-orange color. Argon, another commonly used gas in sign making, emits blue. In the aurora, the elemental colors of green, red, and blue blend together to produce other hues and shades. The wood that fuels this campfire has something in common with the energy of the aurora. Both produce light and heat. And like the campfire, most of the aurora's output is not light, but heat. In fact, almost all auroral energy is dissipated as heat or radio waves. These effects are important, but it's the visible aurora that attracts our attention. And in order to see the light, the skies must be dark.
When people ask me what's the best time to see the aurora, I tell them to, first off, you're going to have to wait for about an hour and a half after the sun sets before it's dark enough to see the aurora in the sky. If you're really pushing and want to just set your alarm clock, then I would suggest the midnight hours, because it's during midnight to around 2 a.m. that the auroras have a tendency to be very bright and very fast motion in the sky. If you're trying to pick the time of year, then I would suggest September and March. For reasons we're not real clear on, the auroras in those seasons tend to be better than they are in December and June.
Some people believe it has to be cold to see a good aurora, but scientists say this is a misconception. However, skies do have to be clear, and clear nights tend to be colder. Geography also plays a big role. Since the best viewing areas for the aurora are in polar regions, night skies during the warm summer months are simply too light. Nevertheless, in a narrow band of subpolar regions, aurora watchers have about 240 nights each year to choose from. Many of these nights are cold, but some of the best, in the fall and spring, require only a warm jacket.
And then this will give you your background.
Tom Hallinan stays awake many clear nights, observing the aurora with a keen and knowledgeable eye. Much of his research examines the shapes of the aurora.
Well, sometimes the aurora is just a diffuse glow that covers the whole sky, but more commonly it's organized into specific forms that are very localized. The most basic and most common form is something that we refer to as an auroral arc, and it's actually a streamer that extends across the sky, and it's something in appearance somewhat similar to this piece of lawn edging. It runs generally in an east-west direction, and it can be 1,000 miles or more in length in the east-west direction. And yet at the same time, its thickness in the north-south direction is very small, only about a mile. The arc also very often has folds very similar to the folds in this lawn edging. And when you view the arc up in the north the way we most typically see it, these folds appear as vertical striations that we refer to as auroral rays. And then as you get closer to midnight, the aurora starts becoming more active, and this basic arc structure starts distorting into large folds that will undulate along the arc. And then sometimes these folds get even more distorted, and we get big spiral shapes like this that may be 1,000 kilometers or more in diameter. This happens to be the way it would appear in the northern hemisphere. In the southern hemisphere, you'd see the mirror image of that.
What any auroral shape looks like depends on its position in the sky in relation to your position on the ground. Here are some tall auroral rays photographed far to the north. And this is how rays might appear if you were looking straight up at the bottoms of them. No one who has seen auroral rays dancing overhead or rippling from one horizon to the other would question the speed of the aurora. That motion, however, is quite deceiving. This movement of the aurora is as deceptive as the motion of an electronic sign. The words aren't racing across the billboard and then disappearing around an edge. Instead, selected lights, much like the atomic collisions in the aurora, are flashing on in a sequence that mimics motion. If observed for many nights, it becomes obvious that the aurora is not haphazard. Similar structures and forms present themselves time and time again. These shapes and patterns are largely influenced by the Earth's magnetic field. Just as the size and shape of the aurora can vary, so can its intensity. Measuring the amount of light given off by the aurora is one of the challenges facing researchers at the University of Alaska's Geophysical Institute. The brightness of the aurora is especially important to Daniel Osborne, project engineer of the Aurora Color Television Project. He spends many of his nights recording the aurora's true motions and colors using an ultra-sensitive video camera.
When scientists talk about the brightness of the aurora, we use a unit of measurement called the kiloraylet. It's a unit of brightness, much like an inch or yards is a unit of length. A 1 kiloraylet arc you can just see with your eye, just barely see. A 10 kiloraylet arc you could see fairly clearly. Think of that as the small night light in your hall shining down the hall through your open bedroom door on the wall. Maybe 100 kilorayleigh arc is the hall light, the 100-watt light bulb coming on down through the open bedroom door, shining quite brightly on the wall. There's that scale of difference between the brightness of the aurora, and it changes quite dramatically very fast. For one interested in watching the aurora, the brightness is very important because it determines whether you can see the color or not. Imagine yourself in your closet trying to pick a shirt out in the dark. You can't tell what color it is. This shirt, for instance, is blue, but in a very dark room you couldn't tell it from a gray shirt.
Drivers living in the north are often lured to the side of the road by brilliant displays of the aurora. For most, it's simply a moment to enjoy color and motion. But for some observers, questions come up. And one of those is, where does the energy come from that can turn on these polar night lights? The answer originates 93 million miles away, at the sun.
There are two very simple, very good clues that tell us that the sun is involved. One is that there's an 11-year cycle in the activity of auroras, that every 11 years you tend to get bigger, brighter auroras that go further towards the equator, seen by more people. And that's the same time when you see more of these black spots in the sun that we call sunspots.
Sunspots, like pushpins on a map, indicate unusually active areas of the sun. The most dynamic are gigantic explosions known as solar flares. These massive flares can trigger spectacular auroras.
The other thing that's even more direct is that when there is a particularly big auroral disturbance, very often there will be another big one 27 days later. 27 days is the apparent rotation period of the sun as seen from the Earth. So those two clues tell us pretty clearly that the energy comes from the sun.
A great red aurora is caused by intense solar activity and is very rare. Few northerners could hope to see more than one of these displays in their lifetimes. This blood-red aurora dominated the skies in March 1989 and was seen by observers as far south as Mexico. The sun provides the energy that creates the aurora in the form of an electrical storm. Blown out in all directions from the sun as a solar wind, this vast stream of electrically charged particles, some of which are aimed at the Earth, travels through the solar system at nearly 2 million miles an hour. The journey to our planet takes 2 days.
Before we can understand how these electrons thrown out by this storm on the sun can create the aurora that we see in the Earth's atmosphere, we have to understand a little bit about the Earth's magnetic field. And the Earth has a magnetic field we're all familiar with using a compass to find the North Magnetic Pole. But actually, it is like a bar magnet embedded in, say, a grapefruit. The magnetic field actually permeates everywhere inside the grapefruit. It's not just straight from the North to the South Pole. And you can do a demonstration with this by using a bar magnet and a piece of paper and sprinkle some iron filings on it. And we have something over here that we can do this with. This is a simple bar magnet. Has a North Pole and a South Pole. If I stick it underneath this piece of paper and sprinkle iron filings on it, we can begin to see not only the bar magnet itself, but as the iron filings fall on the paper, they're starting to form up along the lines of magnetic force that lead from the North to the South Pole on the magnet. These actually extend to either side in far directions. It's along these magnetic lines of force into the polar regions that the auroras occur.
As the electrically charged particles in the solar wind approach the Earth, They are deflected by a gigantic force field called the magnetosphere that is created by the Earth's magnetic field.
It's like a rock in a stream. We've all watched the water flowing past the rock, and a leaf or something won't even hit the rock. It'll actually flow around the rock, but it gets caught on the eddy behind the rock. And in a sense, that's what's happening with the aurora. The electrical energy that's come from the sun is deflected around the Earth pretty smoothly, and most of it goes right on by. But there are turbulent eddies created behind the rock in the stream. And the same is true with this energy from the sun. Some of it gets trapped behind the Earth.
A small percentage of the particles deflected by the magnetosphere become trapped in an eddy behind the Earth. In this area, some of the Earth's magnetic field lines are disrupted, sometimes torn apart. Once trapped, the particles accelerate along the Earth's magnetic field lines and enter the Earth's atmosphere somewhere within the polar regions.
Now, the reason you only see it in the polar areas is this turbulent region behind the Earth. These eddies are tied only to those regions. The remainder of the Earth, around the equatorial regions or even in the very top of the polar regions, are shielded from this turbulent region by the Earth's magnetic field. So we only have auroras as crowns of light in the northern and the southern polar region. Now, it's true that when we have a major or a storm, and just as a crown might sit on my head and have a certain diameter and sit on top of my head, as the auroral storm becomes much stronger, this crown of light can be kind of like a rubber band. It can expand out, and therefore the crown would come down lower. So it is true that in times of really great auroral storms, we do have reports of aurora seen from perhaps the middle part of the eastern seaboard of the United States or middle part of Europe.
The active aurora is stretched around each pole in a gigantic oval. This is a computer-enhanced image of the actual auroral oval over the northern hemisphere, taken by a polar orbiting satellite. The sunlit side of the Earth can be seen clearly, as well as the typical shape of the oval. Looking down at the northern hemisphere, the auroral oval stays parked in a relatively stationary position around the pole. Under normal conditions, observers living near this active auroral zone can see the northern lights. As the Earth rotates, different areas pass beneath the slightly irregular oval, experiencing the typical progression of auroral activity. Observing from the ground beneath the aurora oval is only one way to view the aurora. In 1985, astronauts aboard the shuttle Challenger photographed the aurora from their vantage point in space. The presence of the aurora is due to atmospheric gases and a magnetic field. And as it turns out, we aren't the only planet that fits the bill.
The colors of the aurora in the Earth's atmosphere are unique to the types of atoms and molecules in the Earth's atmosphere. There are auroras on all of the gas giant planets, such as Jupiter and Saturn and Uranus. But their auroras are a very pale red because their outer layers of those planets only have hydrogen atoms in them.
For people in the north, the aurora comes with the territory. Most observers notice only the colorful dance. But auroral scientists know that the same forces that generate these lights in the sky can create problems. The vast power generated by the aurora often disrupts radio and satellite transmissions. The current that is produced by the aurora will actually flow in electric power lines, and it is a direct current rather than the alternating 60-cycle current that power systems are designed for. In particular, A powerful aurora can burn out transformers. Shortly before midnight on March 13, 1989, the people of Quebec were cut off from the rest of the world by a massive 6-hour power outage. The culprit was a huge blast of electricity from this dazzling blood-red auroral display that wiped out the province's power system. The same display also burned out the main transformers in a nuclear power plant along the Delaware River. Scientists can also measure underground electrical currents produced by the aurora. These currents can flow in or out of a metallic object and cause corrosion, a potentially serious problem, especially for the hundreds of miles of the Trans-Alaska oil pipeline which are buried. The pipeline company had to take the aurora into account when considering corrosion resistance. To some, looking at the aurora warms the heart and the soul. To others, it does even more. It fires the intellect and lights a path to be followed in a quest for knowledge.
As a youngster growing up, I was fascinated with space. I read science fiction. I knew that I wanted to be involved in something to do with space. The aurora has provided me with the opportunity to do it, and I've had the opportunity to contribute to scientific research. But the bottom line is, it is so majestic and dynamic that becomes the reason you study the aurora. I love it.